Anybody has any question? Okay, so let us start today's lecture. In the previous class, we were discussing about bearing capacity theories, which include limit equilibrium method, Skempton's method, Prandtls method. So those are a very primitive and initial bearing capacity theories developed by different people. Then the original theory was developed by Terzaghi. So that's why it is called as a Terzaghi's bearing capacity equation. However, there were some limitations in Terzaghi's bearing capacity equation. So a couple of them are: first, Terzaghi's equation is valid only for the strip footing. It doesn't account for if the footing shape is a square or a rectangle or a circular or so on and so forth. Although he has given or the Terzaghi's equation has been modified, so depending upon the shape of the footing, but still it has other kind of limitations, such as, so it is not useful if the load is inclined or if the footing is subjected to axial load as well as the moment, or if base of the footing is inclined itself, or the location of the footing is on the sloping ground or on the ground surface. So these are a couple of limitations of the Terzaghi's theory, and these limitations are overcome by Meyerhof. So that's why Meyerhof theory is called as generalized bearing capacity equation theory. So Meyerhof tried to incorporate whatever the limitations are there in the Terzaghi's equation in the form of another factors. Those are called as shape factor, depth factor, and the inclination factor. Subsequently, the Meyerhof equation was further extended by Wisick and Hansen, and in fact these equations were also further extended by various different people, but we don't use them much. So we majorly use the generalized bearing capacity equation, that is Meyerhof or Wisick or Hansen. So these three theories are prevalently used for the calculation of bearing capacity equation. So in the last class, we also attempted to understand how the Meyerhof theory, the shape and depth factors are differs than the other theories such as Wisick or Hansen. So for better understanding, again you can see in this slide the shape factors proposed by Meyerhof as well as Wisick and Hansen. So Meyerhof theory, the shape factor, he has suggested for two things: when the angle of internal friction is 0, which is nothing but for pure clayey soil, the lambda Cs is 1 plus 0.2 into B by L. When the soil is pure clay, then the lambda S and lambda gamma will become 0. We also did try to understand there are three terminology involved in bearing capacity equation: CNC plus QNQ plus half gamma D and gamma, where the first term is called as the cohesive term, and the second term is called as the overburden term, and the third term is called as a self-weight component. Accordingly, the shape, depth, and inclination factors were inbuilt in all the three terms in the form of SC, SQ, S gamma. Those are shape factors. DC, DQ, D gamma. These are depth factors. Then IC, IQ, and I gamma. So these are inclination factors. So here in this case, you can see for pure cohesive soil how to determine the shape factor when use bearing capacity theory or when you are going to use Wessick or Hansen's theory. And if phi greater than 0, that is phi greater than 10 degree, so then these are the equations you're supposed to use for calculation of the bearing capacity. So these are the depth factors for Meyerhof theory as well as for Wessick and Hansen's theory. Again, for Meyerhof, depth factor for pi is equals to 0 and for pi greater than or equal to 10 degree for both the cases. While Wessick and Hansen proposed the depth factor as a function of df by b, which is a critical parameter to decide whether the given foundation is a shallow foundation or a deep foundation. So this is also one of the core assumptions in Terzaghis theory. As per the Terzaghi, a foundation is called as a shallow foundation if df by b is equals to 1, which however later modified by Meyerhof, and now it is said that so it can be called as a shallow foundation up to df by b is equals to 4. So if it is above 4, then it can be treated as a deep foundation. Then another variety of inclination factor, another variety of factors are inclination factors. So as given here, so again there is an inherent assumption. So in these inclination factors, if the load is vertical or 90 degree, you supposed to take all inclination factor values as unity, which otherwise it overcomes or it becomes some kind of a limitations to the Meyerhof equation. So this is only the another assumption or one of the assumptions in the Meyerhof theory. We also try to understand, so the Meyerhof theory is valid equally for the shallow foundation as well as deep foundation. Similarly, even Wessick and Hansen equations are also useful for calculating the bearing capacity of a deep foundation. So in addition to the three factors which were highlighted in the previous slide, that is shape factor, depth factor and inclination factor, there are other factors also proposed by the different people, which include ground inclination factor, then base factor, then rigidity factor. So although the shape, depth and inclination factor are especially shape and depth factors are most common, if the load is inclined, then we use load inclination factor. But in cases where the footing is located, especially on the sloping surface, or if the footing itself is some kind of an inclined location or inclined, then we use additional factors. Those are called as a ground inclination factor. This indicates that the slope is not horizontal, rather it is inclined. Base factor, whether the base is horizontal, base means it's not a ground, the base of the footing, the ground may be horizontal, but the base may be either horizontal or inclined. So accordingly, you have to take into account another factor that is called as a base factor. Then rigidity factor. So this is also another factor depending upon whether the footing is rigid or flexible, or the soil is rigid or flexible. So we did understand about the shape factor, depth factor and inclination factor equations. There are also equations for ground inclination, base and rigidity, so which I will not discuss here, maybe because these are some specific cases while above three are general. So if you know the general conditions, so those are good enough for undergraduation level. So the other things you can refer to any of the book. What are these inclination, these factors or equations for these factors? In case if you are encountering when you joined in a job, then accordingly you can incorporate. So then having said about almost 6 variety of factors, then if you try to write the ultimate bearing capacity equation, so that equation something looks like this. Q ultimate is nothing but CNC DC CNC SC DC IC GC and BC. So C is the cohesion, NC is the bearing capacity factor, SC is safe factor, so C is the cohesion, NC is bearing capacity factor, SC is safe factor, DC is depth factor, IC is inclination factor, GC is ground factor, and BC is base factor. So this is called as the cohesion term. The second term is called as overburden term. So here Q is nothing but your overburden pressure, which is defined as gamma times of dF. Again NQ, this is another bearing capacity factor. SQ safe factor with respect to overburden pressure. DQ depth factor with respect to overburden pressure. IQ inclination factor with respect to overburden pressure. Similarly GQ and BQ ground factor and base factor. The last one is called as the self weight component. So this is, you can see, of gamma B, N gamma, S gamma, D gamma, I gamma, G gamma and B gamma. So where gamma is unit weight of the soil, so rho G multiplication is nothing but gamma. B is the width of the footing, N gamma is the bearing capacity factor. Similarly, you can understand the shape factor, depth factor, inclination factor, base factor and ground inclination factor. So this is the most generalized bearing capacity equation. So in general, the bearing capacity is referred in terms of the factor called as the Q ultimate bearing capacity of the soil. So we have seen the equations for when the footing is subjected to axial load. But how should I calculate the bearing capacity if my footing is subjected to eccentric load or movement or the inclined load, so on and so forth. So let us see. So this is the case which we did discuss. There are two things in general or in reality. You can understand that if from the right side picture, if B is the width of the footing, the location of the column is not at the center, rather at some location. So the distance between center of the footing and the location of the column is generally designated with eccentricity. Now this eccentricity causes, in addition to the axial load, a moment on the footing. So therefore, if you try to draw the free body diagram of a footing with one-way eccentricity, then this is how it looks like, where there is a load Q and with a moment M. So this M can be defined as the Q multiplied by E, the axial load multiplied by the eccentricity. That means we are transforming the original condition into the fictitious condition. In reality, the footing is subjected to the axial load, but when it is converted in terms of the mathematical simplicity, so where the column is again at the center, however, the eccentricity is accounted for in the form of the moment, in the form of a moment. However, though there is a mathematical simplification or transformation from the reality to the mathematical equation form, but in terms of the soil bearing pressure, there is change. Suppose if you look at a footing is subjected to only axial load, then one can ensure there is uniform soil bearing pressure at the bottom of the footing. So this is possible only in case where the footing will be subjected to the axial load. However, in case where the footing is subjected to eccentricity as is shown in this slide, then first thing is that the whole of the footing area, for example, if you take the B is the width of the footing and L is the length of the footing, whole area, that is B by L, will not contribute for soil bearing pressure, will not contribute for the soil bearing pressure. So then what is that area which contributes for the soil bearing pressure, which has been shown in this diagram with this gray hatched area. Now here you can see, since there is eccentricity only in one direction, here in this case it is in width direction, so therefore whole length will be subjected to the soil bearing pressure. However, in case of the width direction, it is not the whole width of the footing, rather the effective width of the footing, which is subjected to soil bearing pressure, is designated as B dash, which is nothing but B minus 2 times of E, where in the length direction whole length contributes for soil bearing pressure. Now if you look at the this right side diagram carefully, you can understand that in case of one way eccentricity, the area which is equals to L dash by B dash only contributes for soil bearing pressure, where the length which is equivalent to 2 times of E, either in the width direction or in the length direction, depending upon the eccentricity presents, then a length equal to 2 times of E will not at all contribute for the soil bearing pressure. Okay. Now, depending upon the value of the eccentricity, so the footing will be subjected to two variety of stresses, that is Q max and Q minimum. Now, this Q max and Q minimum is contrary to the case of the footing subjected to the uniform axial load, that is Q average. In case of the Q average, the soil bearing pressure is uniform throughout the width of the footing. While in case of the eccentricity, it is Q max on one side and Q minimum on the other side. However, the development of Q max and Q minimum is again dependent on the intensity of eccentricity, where this is typically represented in the form of B by 6. This is called as a middle third rule. Now, it may so happen that depending upon the eccentricity, the Q max can go as high as, but Q minimum can also be lowered down to 0, or even negative. So for a better understanding, people did work or did try to derive under what condition the Q minimum becomes either 0 or negative. So that happens if the eccentricity exceeds b by 6, meaning thereby if the location of the load is outside, suppose say this is the footing, this is the footing. So I am dividing this footing into uh, three sections. This is b by 3 and this is central b by 3 and this is the another b by 3. So the meaning of this b by 6 is that if the location of the load is outside the central portion of the b by 3, then there is a possibility that the Q minimum becomes 0 or negative. Now, what do you mean by negative here? Negative means there is a separation of footing from the bottom soil. When there is a separation, you can presume that the condition looks like this. Say this is the footing. So this is the footing and say, so this is the ground surface. This is the ground surface. In case where b by 6 is greater than E greater than b by 6, then we can see that the ground is something like this or the footing is something like this. Oh, sorry. So this is the ground surface and this is the footing. Here you can see this is called as a separation. Separation. This separation is termed as the tension. This separation is termed as tension. So since the separation is not acceptable, that is why it is called as a the tension is not allowed in case of the footing. So I hope it is clear to you everyone. So if you have any questions, please ask me. Anybody has any question or difficulty in understanding the footing with one-way eccentricity? Anybody has any question? Okay. Okay. So this is the pictorial depiction of the same footing with eccentricity. So in terms of the middle third rule, where you can see, so this is there is a development of Q max, Q minimum when it is just on the border of middle third. So this is one middle third, this is another b by 3 and this is another b by 3. When location of the footing is on the verge of middle third, then the Q minimum becomes 0. If it is inside the middle third, inside b by 3, then there is a Q max and there is a Q minimum. But if it is outside the middle third portion, then the tension or separation between the footing and the soil happens. So that is not at all allowed. So this should strictly be
Sir, that is
avoided.
middle third or B by 6?
This itself is called as a middle third rule. B by 6 on one side, B by 6 on the other side, on another side. So B by
Okay.
6 plus B by 6 is B by 3. See, for example, if you look at here, so this is one B by 6 and this is another B by 6. So total is B by 3. So then, though we did discuss about there is a possibility of development of the maximum and minimum bearing pressure, then how do you calculate Q max and Q minimum? So these are the equations. So these equations were developed based on your bending theory, where it is, if I remember, M by I is equals to E by Y is equals to, I think, what is the third one? No, this is not
E
E.
by R.
E by R. Yeah,
Sir,
this is
last one, E by.
last one is E by R, and this is F. This is not E. M by I is equals to F by Y is equals to E
Sir,
by
it's sigma by Y, sir. It is sigma by Y.
ah, sigma Y by Y is equals to E by R. Now this is called as a bending theory equation. If you take the first two terms, M by I is equals to sigma by Y, so then you try to inbuilt all these parameters, because you know M is a moment, which is nothing but Q times of E. I is moment of inertia, since uh, that depending upon the shape of the footing, you can take BDQ by 6 or BDQ by 12, whatever it is. Sigma, that is stress beneath the footing, and Y is nothing but your eccentricity. So if you substitute everything in the form of a stress equation, sigma, which is nothing but m y by I, my by I. So m is the moment, which is nothing but q times of e, q times of e. So y is that is centroidal distance, then I is moment of inertia, that is bd square by 6 or bdq by 12, whatever it is, depending upon the shape. If you substitute and simplify, what you get is sigma is nothing but 6m by b square into L. That means when you deal with the eccentricity cases, you have a two independent fact terminology: the stress because of the axial load and the stress because of the moment. So in case of the Qmax, it is a plus stress due to the axial load plus stress due to the moment. While in case of the Q minimum, it is minus stress due to the axial load minus stress due to the moment. Or in general, it can be written as Q is nothing but Q by BL into 1 plus or minus 6E by B, where if you substitute in place of M or Q, E is nothing but M by Q. Since we know the axial load on the footing and we don't know the moment, so if you want to know if you want to calculate the eccentricity, then use this equation. Substitute E is equals to M by Q here and simplify. What you get is Q by BL into 1 plus or minus 6E by B. So this equation can be used in two ways. If I know the eccentricity value, I can able to calculate the maximum and minimum bearing pressure beneath the footing. Or alternatively, suppose if I know Q max and Q minimum, then I can calculate what would be the allowable eccentricity. So either way it is useful. Okay, but here although it is shown the stress due to the axial load, that is Q by area, that is B into L, but as I have discussed in the previous slide, we cannot take the width and length as it is. Rather, we need to take one of the dimension in a reduced way. That is why it is called as a effective area method. So in case of one-way eccentricity, the method that followed for the calculation of the bearing capacity is called as a effective area method. So since one dimension, either L or B, so here it is shown L is taken as a L, but B is taken as a B dash, which is nothing but B minus 2 times of eccentricity. So B minus 2E. Since the width is reduced, then there is an increment in the bearing pressure, that is Qmax. So these are the steps which should be followed for the calculation of the ultimate bearing capacity.
Sir,
First, yeah,
sir, last equation how it reacts, sir?
last, can you please repeat your question?
So this Qmax equal to 4Q by 3L B minus 2.
You don't need to remember this equation. This is simplification. Forget about this equation.
Sir, means if I put B is equal to B minus 2 in Qmax, then it is not coming then.
Yeah, it will not come. That is true. That's why I said forget about this equation. This equation is only meant to say how to replace L and B dash. Okay, so let me give you a clear idea in this slide. Now, when you are dealing with the footing with one-way eccentricity, the first step is you need to calculate effective width and effective length. If you found that the eccentricity exists in width direction, then effective width is nothing but B minus 2E, and your L dash becomes L, doesn't matter. While it may become reverse if the eccentricity exists in the length direction. In that case, your B dash is nothing but B, but L dash is nothing but L minus 2E. So therefore, you need to be little attentive when you are reading the sum. Try to identify in which direction the eccentricity exists, either in the width or in the length. But the effective width or effective length concept must be applied only either to the width direction or to the length direction. So as is demonstrated in this slide in step number 1. In step number 2, if you look at the equation also, so the Q ultimate is nothing but C and C, SC, SD, NC, DC and IC plus Q and Q, depth shape factor, depth factor and inclination factor. Now if you look at the third term, that is B, now do not replace B with B dash in the last case. Okay, to evaluate FC, FQ, F gamma, these are shape, depth and inclination factors. Use the relationships given in table 3.4, because if you look at the shape, depth and inclination factors, there also there is a length and there is an width factors are involved in it. So therefore, in calculation of all your shape and depth factors, use effective length and effective width dimensions instead of the original given dimension, that is L and B. To determine FCD, FQD and F gamma D, use the relationships given in table 3.4. However, do not replace B with B dash. So the meaning of this one is that when you are calculating the shape factors, you must use the effective length and effective width. While when you are calculating the depth factors, do not use effective width or effective length. Okay. While in case of the inclination factors, you don't need to bother about width or length because it is only the inclination that matters. And third important point is in the ultimate bearing capacity equation, instead of the B, use B dash. Okay, so now I will repeat. There are three important points that I have highlighted here. First important point is when you are calculating the shape factor, use effective length and effective width. When you are calculating the depth factors, so use the original length and original depth. Do not use effective width or effective length. The third important observation is in the ultimate bearing capacity equation, in the third term, that is self weight term, replace B with B dash. So these are the three important observations you must remember. So when you are dealing with footing with one-way eccentricity. So then here there are two parameters that has been given. One is small QU and there is capital QU. Small QU nothing but this is the ultimate bearing capacity, while capital QU is nothing but ultimate bearing load. If it is a load, you must represent with the capital. If it is a stress, you must represent with the small q. So your load is nothing but total stress divided by the area. That's it. And when you calculate the ultimate load on one-way footing or footing with one-way eccentricity, again you try to use the effective length and the effective width.
So
So the
this
last one,
QU should be in numerator or denominator, sir?
this is load na. Your load is nothing but stress multiplied by area. No, actually this is not a numerator or denominator. Sorry, don't misunderstand. This is not a numerator or denominator. Here it means to say this B dash by L dash is nothing but A dash. Q ultimate, capital Q ultimate is nothing but QU dash multiplied by B dash multiplied by L dash. If you look at carefully, so this is bar. This is not a numerator or denominator. So the next one is footing with inclined load. So again, I repeat, how to distinguish footing with inclined load and footing with the eccentricity condition. If the footing is in eccentric condition, the location of the column is somewhere here. While in case of the inclined load, the column itself is inclined or the load application itself is inclined. Now here in this case, one of the general mistake done by most of the students is where should be the bottommost tip of this arrow of the inclined load. Remember that this always must be at the bottommost of the footing. Often it is represented with the arrow at this location. So this is wrong. This doesn't fall under the category of footing with inclined load. Only this is the right. So when the column location or this capital Q ends at the ground surface, this again falls under the category of footing with eccentricity or footing with the horizontal load or footing with the moment. Because here in this case, where the load inclination is terminating at the ground surface, this can be resolved into the force can be resolved into two things, the horizontal and vertical. Okay, so in case of footing with inclined load, such assumption is not valid because the inclination is directly taken into account in the form of a inclination factor. So in this case, inclined loads, one thing is certain that, so when you calculate the bearing capacity factors, so what you need to do is you have to use the inclination factors. Where earlier in case of the axial load, all Fc, Fq, F gamma is taken as a unity, but in case of footing with inclined load, the values of the SFC, FQ and F gamma must be computed, where this beta is inclination of the load with respect to vertical. So as is shown in this left side schematic. So these are the remaining all. There is no change in the shape factors. There is no change in the depth factors. They will be as it is. And there is only additional term that comes into the picture is the calculation of inclination factor. So then these are the equations. So Q ultimate is nothing but C NC SC DC IC. So this is with respect to length. Again, when we talk about the inclination, is the inclination is with respect to length or with respect to width. So here with respect to width, here with respect to length. So therefore, you need to calculate both of these things if it is given. If it is not mentioned, so there is no problem. Or in general, it is advisable to calculate Q ultimate with respect to width and with respect to length, and whichever is the least, that shall be considered as the bearing capacity of the soil. So the value of smaller value of Q ultimate computed by either of these equation. Okay, so the form of the equation is remained same, say in case of the axial load or in case of the footing with one-way eccentricity or footing with the inclined loads. But how they have been incorporated into these equations has been demonstrated so in all previous slides. So apart from that, so there is nothing additional to be discussed about the inclined load. Okay. So now we did discuss about how to calculate the bearing capacity when the footing is subjected to axial load, inclined load, eccentric load. So these are the three conditions. But the footing is located on the soil on the natural ground, where within the natural ground there is a groundwater. So as we have studied through soil mechanics, we know what will be the impact of groundwater or water within the soil mass. So in fact, I have also said if there is no water within the soil, we don't need to read about or study about the geotechnical engineering at all. So it is only because of this groundwater numerous subjects have been evolved. Now let us try to understand what will happen to the bearing capacity if there is a change in the groundwater table. First of all, through your soil mechanics, you did understand what happens to the total stress, how the stresses will get transformed from total to the effective when you change the pore water pressure condition. So it is clear from your soil mechanics, total stress is nothing but the total load borne by the soil as well as the water. But when you talk about the effective stress, it is exclusively said that in case of the effective stress, it is only the load borne by the soil particles, but not by the water molecule. Now, how to understand this groundwater effect? First of all, in your consolidation theory, you understood that if any amount of load is applied, there is something called as consolidation phenomenon taking place. That means change in the volume of the soil. But here also same thing is happening. So here this is the footing and this is the ground surface. So the footing is located at some depth from the ground surface, that is called as a DF, and this is the soil. So this entire soil mass is subjected to the stress condition. Now as a result of this stress, or this stress can also be designated with delta sigma dash. So the same term which you used in case of the consolidation equation. So if I write your consolidation equation, SF is nothing but Cc into H divided by 1 plus E naught. So log so sigma naught dash plus delta sigma dash divided by sigma naught dash. Now Cc is coefficient of compression. So this is the slope of E versus log sigma graph, that is your consolidation. So this is nothing but your Cc. E naught is initial void ratio and H is thickness of the soil layer. So this is H, thickness of the soil layer which is under stress. And what is sigma naught dash? That is initial effective overburden pressure, sigma naught dash. So this is in fact from the ground surface, not from the footing location. And your delta sigma is nothing but, so the increment in effective overburden pressure. Suppose if I remove the delta sigma term from this equation, then there is sigma naught dash by sigma naught dash. So this will become log of 1. So log of 1, as you know, what will be the value of log of 1? Then accordingly you can calculate the final settlement. Okay. So if any value that you are getting without delta sigma, that value is called as a self weight consolidation. But when you construct a footing within the soil, as a result, you are imposing an additional load, that is this delta sigma. And because of this delta sigma, there is change in the settlement. And this settlement should not exceed certain value. And when you impose the delta sigma, there is something happens within this soil volume, that is change in the pore water pressure. That means there are changes in the stresses from sigma naught to sigma naught dash. There is initially total stress, then it is slowly gets transformed to the effective stress with reduction in the pore water pressure. That is how your settlement increases within the soil sample. That means as you change the location, or as there is a change in the groundwater, which has an obvious consequence in the form of change in the settlement. So as demonstrated through all these equations. The other effects of groundwater are reduces apparent cohesion that takes place when soils are not saturated. So may necessitate reducing the cohesion measured in the laboratory. Then the groundwater increases the pore pressure as I demonstrated here, both effective stress and shear strength in the soil. So that means if there is an increase or decrease in the groundwater table, there is an increase or decrease in the shear strength and effective stress. Consequently, so there is a change in the settlement. So that's why the
Sir, how
effect,
it reduces shear strength of the soil, sir, for water percent?
as you can see,
Sir,
there is something called as a cohesion. Cohesion means it is electrochemical or some kind of the chemical bonding between the soil particles. So when water is introduced into the soil media, so that dissolves or weakens that chemical bonding. So since cohesion is a bonding, the reduction is bonding is nothing but the reduction in the shear strength. Because
okay.
you got my point now? The shear strength is represented in terms of
Okay.
cohesion and angle of internal friction. So this is the effect of the groundwater. Now here 4 cases have been taken to understand what would be the impact of the groundwater on the bearing capacity. Now we have seen the bearing capacity equations that is remains same. Let us talk about case by case. Shall I stop it here or shall I continue? Okay, so let me discuss the groundwater effect in the next class. So I will stop it here. It's already 9:57. So we have a couple of minutes. If you want to ask 1 or 2 questions, you are most welcome.